All right, let's look at chapter 15, the last chapter of the semester, radical reactions. Okay, little introduction. First, radicals are very reactive intermediates with one unpaired electron. And we draw radicals by putting this little dot on the carbon where that unpaired electron is, just like a Lewis dot structure. So this right here would be a primary radical. This is a secondary radical. 3 R groups on the carbon containing the unpaired electron would be a tertiary radical. Note that each of these carbons is sp2 hybridized. The unpaired electron is in the unhybridized p orbital on that carbon. All right, and also note, similar to carbocations, that primary radicals are less stable than secondary, and tertiary are the more stable, the most stable of these radicals. And yes, no radicals are very stable, but of these very unstable radicals, the tertiary radical is the most stable of them. Okay, now how do you get these radicals? Note, normally when you break a bond, all the bonds we've been breaking when we're doing our reactions are SN2s, E2s, all of these types of reactions. Both electrons in the bond went to the same atom, and if you look closely, you'll see both electrons in the bond went to the more electronegative atom. That is heterolytic bond cleavage. What we need to do now is homolytic bond cleavage. We need to take a molecule and we need to break a bond, but have one electron on the bond go to one atom, the other electron in the bond go to the other atom. And that is not the easiest thing to do, but it will work if both atoms of the bond are the same atom. If they have the same electronegativity value, then you have a higher chance of it breaking homolytically with one electron going to one atom, one going to the other atom, since both atoms have the same electronegativity value. Okay, and that is how we will form radicals when we don't have any to begin with. We have to add heat or light, are 2 ways to break bonds. And sometimes it'll be in the presence of a radical initiator, such as peroxides, and we'll get into that. Now, once you have formed a radical, once you have a radical formed, then that radical can react with bonds, and we do this type of thing. So let's look at these radical reactions. Here's a carbon-hydrogen bond here. If we have a radical like chlorine atom or something like that, where we have one unpaired electron, that one paired electron will react with this hydrogen, and the carbon-hydrogen bond will break. One electron of the carbon-hydrogen bond will go onto the carbon. The other electron will get together with this unpaired electron on our radical to form a bond. So we form the bond between the H and the X here. Note this bond, as we said, one electron came from the radical, the other electron came from the hydrogen, carbon-hydrogen bond, and we are left with this carbon radical also. Note, if you have a non-radical and a radical that react, you always must end with a radical. If you start with one unpaired electron, you must end with one unpaired electron. We call this reaction hydrogen abstraction. And it's a very common reaction in radical reactions, where a radical will take a hydrogen from a hydrocarbon. All right, another reaction is radical addition. If you have a carbon-carbon double bond, we know the pi bond is always the weaker bond. One electron on the pi bond will get together with this electron on the radical to add that X to the carbon here, and the other carbon will get the unpaired electron. Note, a non-radical plus a radical gives us a radical product. But what if we have two radicals? If you have two radicals, those two can get together. This electron and this electron get together, form a bond, and you can get X2. So two radicals make a non-radical. A non-radical and a radical make a radical. And this comes about when we're doing reactions. Note, here's our two radicals here, make X2. When we do reactions, what we find is If you recall from molecular orbital theory, O2, the O2 molecule, has two unpaired electrons in it. O2 is a radical, which means if there's oxygen around, it's pretty reactive. It's going to react with a radical to make this beast over here, and we get rid of this radical. Which means if you have O2 in your solvent, or if there's any oxygen around, it's going to stop a radical reaction, because the O2 is going to react with all of your radicals and make them not non-radicals anymore. So we call that a radical inhibitor. So if you're running a radical reaction in a solvent, you need to make sure there's no O2 around, and there can be some oxygen dissolved in your solvent, even methylene chloride or any of these other solvents, ethers. So you have to deoxygenate, get the oxygen out of your solvent before you use it, because it'll stop your radical reaction. And we can use that for good, because in your body, it's radicals in your body that your body produces naturally that can cause bad things, including cancer. And so vitamin E is an example of a molecule that's a radical scavenger. It sucks up radicals so they might not do bad things to you. All right. And note, because of this, you can actually use O2 or radical scavengers to determine if a reaction goes by a radical mechanism. So if you run a reaction and you're thinking, I'm not sure if this runs via radicals or not, if radicals are made in this reaction, put in some O2, put in a radical scavenger. If the rate slows down, that means yes, radicals were involved. If the rate does not slow down, that means there probably were no radicals, because the scavenger would have eaten the radicals, slowing down the rate. One thing though, and this is very important, when people think of radicals, they often relate them to carbocations, because you see similar things in terms of stability and whatnot, with tertiary being more stable. The thing to remember about radicals, there are no rearrangements with radicals. If your molecule has a primary radical, and you can see, oh, with a rearrangement I can make a tertiary radical, it's not going to happen. No rearrangements with radicals. All right. So let's look at one of the main uses of radical reactions, the halogenation of alkanes. Recall, alkanes tend to make very good solvents. Hexane, a good solvent. Yes, pentane is a good solvent, because the carbon-hydrogen bonds are not very polar, hardly polar at all. We call them nonpolar. Carbon-carbon bonds are, of course, purely covalent, nonpolar at all. So those bonds tend not to break. Carbon-carbon bonds are tough to break. Carbon-hydrogen bonds are tough to just break. So yeah, they make good solvents because they're unreactive. Hydrocarbons, plain old hydrocarbons, alkanes are fairly unreactive. One of the few or only reactions they can do are halogen reactions via radical mechanism. So let's look at halogenation of these alkenes. Note, it's only useful for chlorine and bromine. Iodine is too slow. F2 is too violent. There will be some books that say, oh, you can use F2 in here also, but that's pretty dangerous stuff. The reactions happen too quick, and truthfully, they give you such a mess of products, every product under the sun, that it's just not useful. Okay, but here's how these reactions work. If you take something like methane and Cl2, you just put the two together, nothing's going to happen. However, if you add light or heat to it, you will be able to put one chlorine on this methane and make HCl. We'll go through the mechanism in a bit. Yeah, but if you still had some more chlorine, add light or heat, more chlorine, you could put on the second chlorine on that, put a third chlorine on that, and you can go all the way to putting 4 chlorines on this molecule through this reaction. All right, and that's the danger. If your limiting reagent is your alkane, you are going to get multiple products. You'll make some monosubstituted, some disubstituted. So if you're running this reaction, if you want to stop at the monosubstituted product, make sure that the Cl2 is the limiting reagent. Have a lot of excess methane around such that the further reactions do not occur. So if you want to monohalogenate, have excess alkane. Well, what if instead of methane we did propane here? All right, if you had propane and Cl2, heat or light, radical conditions, then, well, where could that chlorine go? Well, the chlorine could go on one of the CH3s at the end. Note if it was on this CH3 or this NCH3 here, you'd get the same molecule. Or the chlorine could go here. So we could have the chlorine at the end, or we could have the chlorine in the middle. So there are two possible monochlorinated products. Well, what about this one down here? What do we see here? How many different monochlorinated products can there be? Well, we could put it on this chlorine on this carbon here. We could put it on this carbon here, so there's 2. We could put it on this carbon here, so there's 3. We could put it on this carbon here, so there's 4. Note, this H3 and this H3 are bonded to the same carbon, so whether we put it here or here, you get the same molecule. So this reaction would have 4 possible monochlorinated products, which doesn't make that the most useful of reactions, because you've got 4 products you must separate from each other. And what were to happen if your alkane was the limiting reagent? You had excess Cl2. Well, then you're going to get the mono, you're going to di substitute products, you'd get a real mess here. But this will give, if we keep the Cl2 as our limiting reagent, this will give us 4 products. All right, now let's look at the radical mechanism. And this we're going to see a number of times in this chapter, what happens with this radical mechanism, because it is different than a normal mechanism of reaction. And there are really 3 main steps, 3 main pieces of a radical mechanism, with the last piece, the last piece people don't care about as much, and we will find out why that is. But the 3 pieces of the radical mechanism are initiation, propagation, and termination. I'll give you some hints how you can make sure you get the right answers using these steps. The first thing is the initiation step. All right, we don't have any radicals, we need to make radicals. Initiation makes radicals, and importantly, the initiation step, there can be more than one, it can be a couple of steps, will make the radical that's involved in propagation. So the first step, we need to make radicals. If you have Cl2, that's easy. You add heat or light and you generate 2 chlorine radicals. So yeah, that's how it works. The chlorine-chlorine bond is weaker than a carbon-carbon bond, is weaker than a carbon-hydrogen bond. So just mix, when you're looking at, say, this reaction we were doing up here, you literally just take this molecule here, mix it with chlorine, add the light, and the reaction starts. Because as soon as you add the light, the chlorine radicals form, and the reaction can begin. So that's the initiation step, making the radicals. The next is the propagation step. In propagation, the first step in this reaction here, where we're taking our CH3CH2 with a hydrogen on it, so CH3CH3 ethane, and the chlorine radical is going to do hydrogen abstraction to make HCl and the CH3CH2 dot. Note, a radical and a non-radical, we must end up with a radical. We've gone from a chlorine radical to a carbon radical in this step of propagation. The next step in propagation is that alkane radical then reacts with another Cl2 to make CH3CH2Cl plus Cl dot. Okay, here's the deal with the propagation steps. These are only going to work, this will only happen if the concentration of chlorine radical is low. You want a low concentration of chlorine radical to get this propagation to happen. Because the deal with propagation, these repeat. This is what we call a chain reaction or a chain mechanism. And it works if the concentration of your initial radical is low. because at the end of the propagation steps, you remake that radical. We have our chlorine radical is one of the reactants in the first propagation step. We need to remake that chlorine radical at the end. And that is the trick to remember when you're working through these mechanisms. Whatever radical you start with in the first propagation step, you must end with at the last propagation step. You must end with that same radical so it can go back and start the process over again. You will find there are other ways to run the reaction where you think, oh, I could get my product by doing this thing here, but if it doesn't generate your starting radical again, then that is not going to work. You'll get a termination or something like that. Okay, but here's the deal. When you have the propagation steps here, when you have this chlorine radical, as long as the concentration of chlorine radical is low, then swimming in the solution, you might have some Cl2 swimming in the solution, you'll have this guy swimming in the solution, and you'll have your chlorine radical. And the chlorine radical is just going to react with whatever it bumps into. But note, if the chlorine radical bumps into this, we get hydrogen abstraction. If the chlorine radical were to bump into some more chlorine, nothing would happen. Essentially, the chlorine radical would abstract this chlorine to make Cl2 and leave this as a chlorine radical. So the only reaction that will occur is if the chlorine radical bumps into one of these guys. Now, we need to keep the concentration of this chlorine radical low also, because what would happen if a chlorine radical bumped into another chlorine radical? Well, getting ahead of ourselves a little bit, a chlorine radical plus a chlorine radical would make a Cl2. We'd get rid of that radical, and then the reaction would start slowing down and maybe even come to a stop. So we need to keep the concentration of chlorine radicals low such that they don't run into each other. Okay. At this step, this looks pretty obvious. Low concentration chlorine radical, hydrogen abstraction makes this radical. But once we have this radical, why do we need it to react with a Cl2? Well, when this reaction happens, we've got this radical reacts with a Cl2. It will form a bond with one chlorine. The other electron will go on the chlorine, will end with this chlorine radical, and we'll make our monochlorinated product. What would happen if this radical here ran into a Cl radical? Well, two radicals would run into each other. They would cancel each other out. You would not get a radical, and the process would stop at that point. Note, what's the chance, though, that this radical would run into a chlorine radical? Well, as long as our concentration of chlorine radical is small to begin with, then the concentration of chlorine radicals is very small. This radical can't find it. And since this came from a chlorine radical to begin with, the concentration of this at any one time is small. So the chance of this radical running into a chlorine radical is actually not very good. It's a very small chance. There's a much, much higher chance that this radical, this alkyl radical, will run into a Cl2, because the concentration of Cl2 is much higher than the concentration of Cl dot. In this initiation step, we only took a tiny bit of the Cl2 got converted into radicals. Most of it stayed as Cl2. We keep the concentration of chlorine radicals small. And at this step, we made our chlorine radical, so it goes back in here, finds another one of these ethanes, subtracts a hydrogen to make this ethyl radical. Ethyl radical finds a Cl2 and makes this product, and another chlorine radical, which is this chlorine radical, which goes back, and we repeat this propagation step over and over again. And it keeps going and going and going, making HCl and making this chloroethane until you start to get lots of radicals in there, until the concentration of radicals gets high enough, or you just got product and these radicals, that these radicals can find each other and do this termination, or this radical could find this radical and make this butane, or this radical could find the Cl dot and make more product. But note, these termination steps only occur at the very end, when you've got a lot of product made, and then these radicals can't find anything else for hydrogen abstraction. And so that's the point when this shuts down, when radicals can start finding other radicals, and then it'll terminate. And so yes, the problem is though, will you have some of this butane in there? Yes, but it'll be very, very small concentration of butane, easily separated from a reaction mixture. So the things to note: this is a chain mechanism, a chain reaction. It is very, very exothermic, and the initiation step is the slow step. You mix the ethane and the Cl2 together, mix them up, you hit it with the light, and that's the slow step. As soon as radicals start being formed, as soon as that light starts working, or heat, boom, the reaction's over. It is extremely quick once you start making these first radicals. Once these first radicals start being made, boom, propagation, 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 it's over.